Welcome to Albany Technical College. As a student of the Fire Science Technology program, you're enrolled into the Fire Service Hydraulics course. We'll be utilizing a textbook, Hydraulics for Firefighting, second edition, and it is a Delmar Thompson Learning textbook. I'll be your instructor. My name is Don Lay. This course will begin with Chapter 1 as an introduction to hydraulics. And as an introduction, I would like to point out, lay some groundwork, if you will. Hydraulics in this format is a study as an applied science. Through observation and experimentation have come up with some of the reasoning why. Now, there were people in years of ages past, such as names that you've heard of, Ventura and Manali, Pito, and some of those that actually took some of the early theories and placed it into this applied science. It is not a practical fireground hydraulics course. Your training academies at your station, you do practical fireground hydraulics. We're looking at some of the math work, some of the physics behind hydraulics. You'll see various definitions out there. We're looking at hydraulics as being an applied science of a water. It's what we utilize in the fire service 99% of the time. Even though we add additives to it, that's the fluid that we're concerned with. And we're either storing it to have potential energy, or either we put it into motion. So some of the subdivisions there of hydraulics: hydrostatics, study of water at rest or stored potential energy, and hydrodynamics, the study of water in motion. History goes back to a point where we begin to look at applied science and water supply needs. 1889, it goes that far back. 1910, the National Board of Fire Underwriters, which we know today as ISO, and they published the first fire flow recommendations and requirements at that time. This name you'll see pop up as the father of fire service hydraulics, Fred Shepard. And the textbook, it's out of print, but it's still available in various places there. And it's a good text if you get your hands on it. Practical Hydraulics for Firemen. Let's look at the 10 physical properties of water. And it's identified in your text and begins on page 4. Some common sense. We know that matter is found in 3 states. So water can be found as a liquid. It can be solid state as ice, or we'll also find it in humidity as a vapor state. It speaks of its density of water, where it's pointed out as a physical property at 38 degrees is a point at its densest. It also talks about how much space a cubic foot of fresh water weighs. If you take a cubic foot and fill it full of water, you've got a weight of 62.4 pounds. And it also identifies that salt water weighs 64 pounds. And before we go into some of the physical properties of water, let's review some principles here that might be just that in a review. But let's review something as far as dimensions. If we look at length times width, and you get a figure, and you multiply the two, then we come up with a figure of square feet. If we take a 1 foot square, then 1 foot by 1 foot is a 1 foot square. If we look at it as a bottom of a base here, we know that 1 foot is 12 inches. So 12 times 12 is 144. 144 square inches in 1 square foot. If we take that further and look at a cube, now we have length times width times height. Again, 1 foot by 1 foot by 1 foot is 1 cubic foot. 12 inches by 12 inches by 12 inches. 144 times 12, that's 728 cubic inches in 1 cubic foot. cubic foot of water contains 7.48 gallons. How do we know that? These are examples that are in your textbook. You notice that on your screen you're looking at a Promethean board that I'm using in a classroom setting, and we're using Camtasia as the voice. If we take this cubic foot in a laboratory setting and we pour 1 gallon of water into this, it will occupy a space of 231 cubic inches. If we know that this container will contain 1,728 cubic inches when it's full, and we know that 231 cubic inches is 1 gallon, then through division, dividing 231 into 1,728, we can come up with 7.48 gallons. If 231 is 1 gallon, then 231 into 1728 will give us that figure that's listed in the book as a physical property. Cubic foot of water contains 7.48 gallons. And hopefully that you will, if you have not already, if you're a student in the fire service for some time, you have already through rote memory memorized some of these physical properties. And it's to your advantage, if you haven't done so, to begin to memorize some of these as you begin to go through examples and problems. It'll be to your advantage. A gallon of water weighs 8.34 pounds. Do we know how much Look at the example on page 5 in your textbook, example 1-2. If a cubic foot of water weighs 62.4 pounds, what does a gallon weigh? And you'll notice that through experimentation then that you can take that cube, put it on a scale, zero the scale out, then take that water, pour it into that till it's full, and you've got a reading of 62.4 pounds that cubic foot of water weighs. We've already determined what have we determined to this point that could give us some way if we know that there's 7.48 gallons in this cubic foot, and we know that the whole container full of water weighs 62.4 pounds, then we can divide 7.48 into 62.4 and come up with the figure of 8.34. What is that? 8.34 pounds. 1 gallon of water weighs 8.34 pounds. This should be reviewed, and I don't want to bore you with a review. You'll notice through the textbook, though, that if we're going to make an applied science, then let's look back and see where. I found in the past a lot of times when we walk into a training station or our training officer sits down, he gives us figures to work problems with, but we don't look far enough ahead to know why, where we got that, and that's what the author's trying to do. We know boiling point of water is 212, freezing point is 32 degrees Fahrenheit. And there's a couple more properties of water that we ought to look at. This one maybe you haven't seen before. And we don't see it on the fire ground. A triple point is a laboratory setting here. Water at 32 degrees Fahrenheit at 0.08 pounds per square inch of pressure. At that point, now we're not going to be able to get that except in a laboratory setting, but if we put water at that pressure, then we'll find water at all three states of matter at that point, and it's called a triple point. And also water is non-compressible. And that's why we don't use water in hydraulics fluids, in our transmission fluids or any other hydraulic fluid, because it's non-compressible. We can't get work out of it as far as that compression. So that makes sense, doesn't it? Okay, we've discussed the 10 physical properties of water, and you can go back, and you need to go back and review those 10. And again, if you will, there are some rote memory involved here. If you'll look at some of those physical properties and memorize those, it will be helpful to you as you continue to do the problems at hand. Now let's look at the 4 specific properties. It'll be a total of 10 physical properties and 4 specific properties of water. Let's jump down to this one first, and then we'll go back. Water expands at a ratio. This expansion ratio of water at 1, now the author later will tell you, but that 1 is 1 cubic foot. 1 cubic foot of water will expand 1,700 times when converted to steam at 212 degrees Fahrenheit. And of course it makes sense that at higher temperatures this ratio is going to be higher. This expansion ratio will give us a chance to look at a problem, and let's do that. On page 7, you've got example 1.3. And because of the fact that we are going to a fire ground with our trucks with gallons of water, that's why we're constantly changing and converting cubic foot to gallons, because we don't speak of putting water in the amount of cubic foots per minute. We talk of gallons per minute. But we've got to get through those steps there. And that's why we started off with some volume issues there when we drew out a cube and showed you a volume of 1 cubic foot. This problem here says if water expands 1,700 times going from a liquid state to a vapor state, how much steam will be created by 1 gallon of water? If we know that this 1,700 is an expansion rate per cubic foot, 1 cubic foot, what do we know about how many gallons is in a cubic foot? We know there's 7.48 gallons per cubic foot. So it's a matter of division. If we divide 7.48 into 1,700, now we come up with 227.27. So 227 cubic foot of steam per gallon. And that can, later on, you can see where that would be useful, because we go to the fire with gallons per minute being put onto the fire. And with this 227 expansion ratio will come in handy. Now we've got a word here. We're professionals. Let's learn the word. Enthalpy. Enthalpy is a scientific term that possibly some have never run across before. If you haven't taken chemistry at all, then you haven't seen the word. Enthalpy. Enthalpy of fusion and enthalpy of vaporization. This enthalpy is the amount of heat absorbed or given off by a substance when it changes state. And we're changing the state of water, aren't we? We're changing water from a liquid to a steam, and so something has happened here. And that's what we need to talk about, this enthalpy process. And it is, again, a scientific term and not a term that's been utilized in the fire service. So let's just look at the author's explanation before we go any further. On page 9, he's got, and when you're going through these books, don't bypass those fireground facts, because the author has spent some time in research here of some things that need to be brought to attention. Enthalpy or latent heat, right there on page 9 in fireground fact. I'm just going to read here. I'll try not to, but I want to read something here. Many non-technical sources refer to enthalpy as latent heat. The technical correct term is actual enthalpy. You cannot even find the term latent heat in any self-respecting chemistry book. If you'll remember, every fire book you've possibly looked at has talked about not enthalpy of vaporization, but you've heard the term latent heat of vaporization. That term, latent heat, And I looked it up, and I tried to find out why the fire service even came up with that term latent heat. If we look at the term latent, in psychology it's repressed state, a latent repressed state, and in forensic science we talk of latent fingerprints, hidden. So I'm not sure why the fire service ever come up with a term latent heat of vaporization. We are talking about an applied science course, so enthalpy is what you'll learn from this point on. And if you want to continue in this line of science, look it up. Anybody, I'd love to see some discussion questions out there about that, why you think the fire service ever even come up with the term latent heat of vaporization. It's an enthalpy of vaporization. So we need to look at both of those and see what is happening. If we're talking about a liquid changing state or any substance changing state and how much BTUs it absorbs or gives off in that change, enthalpy of fusion, that's from a solid to a liquid. We don't go to the fire with ice, but yet it's scientific, so we need to know that. Enthalpy of fusion is changing from a solid to a liquid. Ice in the form of a solid changing to melting to a liquid. 143.4 BTUs of water is absorbed in that process. But we do go to the fire with a liquid, so latent heat vaporization. When you change that water from a liquid state to a steam, now that's an important concept to us. 970.3 BTUs per pound of water. That's important to us. So let's look at some of the terminology before we go any further. We'll go back and forth. And as you follow the book there, you'll see I'm not following the book, but you'll take care of that in your studies. A BTU, British Thermal Unit. We constantly see it in the fire service. Amount of heat needed to raise temperature of 1 pound of water, 1 degree Fahrenheit at 60 degrees Fahrenheit. And the ambient temperature of water won't always be 60 degrees, but sometimes it might be 58, it might be 62, but they're using 60 in a laboratory setting. And also remember that we don't talk about taking so many pounds of water to a fire. We talk about gallons. So that's why we're changing. We know how many gallons, and we'll do some more of that work. And when you see that math work, it's going to be necessary. BTUs then. Remember that when we get on further. Enthalpy, the amount of heat absorbed or given off by a substance when it changes its state. So when you change water from a solid, which is ice, to a liquid, we've already seen how many BTUs it's absorbed or given off. And then when you change it from a liquid to a steam. So we know it's available in 3 states, and we've got to change it. Enthalpy of fusion from a solid to a liquid. Enthalpy of vaporization from a liquid to a steam, water going to a steam. Specific heat. Amount of heat in BTUs required to raise the temperature of 1 pound of substance, 1 degree Fahrenheit. Let's look at some problems so we don't get lost in this concept of just terminology. How does that terminology relate to us in the fire service? How can we, what good is it? What good is it? Here's a question, page 8 in the textbook, example 1.4 down at the bottom. How many BTUs will it take to raise 1 gallon of water to 212 degrees Fahrenheit but not vaporize it? Let's stop just a minute when we're talking about steam and water vapor. When we talk about steam, we said that 1 cubic foot of water will expand 1,700 times. When water expands, what do we see? We see steam at a fire. When we put water on the fire, that steam will expand 1,700 times. But is steam water vapor? Think about it. Water vapor is invisible. When we think of water vapor, it's an invisible gas. Steam is not invisible. Steam is visible. So it's water droplets that have been converted, and the currents of the air, because we know we got a lot of currents of air movement in this fire going on. So as that steam expands out 1,700 times, is water droplets. It's not water vapor. Let's get that. So what is an example of water vapor? Humidity in the air. And again, remember we talked about a triple state, one of the specific properties of water. In a laboratory setting, if you take water at 32 degrees Fahrenheit and you compress it at 0.08 psi's, then it's found in all three states, in a liquid, solid, and vapor. So in the atmosphere, there is atmospheric pressure and relative humidity depending upon the pressure, and we know that we either feel hot or cool depending on that. And that water vapor, just keep in mind that we don't want to misuse the terms there. Let's think about the difference between steam and water vapor. And the author is explicit about that, and you'll see, again, in Fireground Facts when you see that. So the question was, how many BTUs will it take to raise 1 gallon of water to 212 degrees Fahrenheit, but not vaporize it? So what's going to happen, it's going to change to a water steam before it goes to a water vapor. And that steam is what's going to help us in the fire service. And we know that. And notice that he's worked the problem out for you, and we'll do the same thing. If 1 pound of water, we're talking about 60 degree at ambient temperature that we go to the fire, or to this particular case, we're raising 1 pound of water. We've got 1 pound of water. We're raising it 62 degrees to 212 degrees Fahrenheit. What does that require to do that? We talked about specific heat. It requires specific heat in this process. So 212 minus 62 is what, 150? And what is that? What do we know about specific heat? 1 BTU raising one, we'll look back. Specific heat, amount of heat in BTUs required to raise the temperature of 1 pound of substance 1 degree Fahrenheit. So how much did we just raise the temperature? 150. So 150 BTUs. Is that helpful? Well, let's think about it as we continue. It goes to a fact of sometimes we think of water being the best substance to go to the fire. Well, there's a reason why. Now, the problem calls for the specific heat, the amount of BTUs for a gallon of volume of water. So far, we know that 1 pound, going from 62 degrees Fahrenheit to 212, we've got this, 150 BTUs. The problem asks for a gallon. How many pounds per gallon? How much? 1 gallon weighs what? Again, we talked about if you memorize through, it should be already there. You should know that 1 gallon of water weighs 8.34 pounds. So what can we do? Can't we multiply 8.34 times 150 and get what the author has already worked out for us here? 1,251. What is that? BTUs going from ambient temperature. From ambient temperature of 62 to 212, we've got 1 gallon of water then will absorb 1,251 BTUs. That's helpful to us in the fire service. We're cooling a fire. And the cooling effect of water we know is important, but now we're coming up with some reasoning behind that. 1 gallon of water will absorb 1,251 BTUs going from ambient temperature of 62 degrees to 212. And the problem has worked out. So you see why we're concerned about using the word enthalpy. Amount of heat absorbed and given off by a substance when it changes state. Water in a liquid state sprayed upon a fire that we know is well over 212. We've got as much as 1,100 degrees Fahrenheit in certain places there. We've got intense heat there. So we're changing that state, and how much are we absorbing? We just come up with a now something that you can, again, put to your rote memory and utilize it later on without having to look it up. Enthalpy of vaporization. Look back again at that definition now that we've talked about those three terms. We're looking at BTUs, what enthalpy is, and specific heat. Let's go back and look at the definition. And you see I'm flipping it up through charts here. Enthalpy of vaporization. Amount of heat absorbed when water goes from a liquid state to a vapor state. And we just looked at 1 gallon of water absorbing 1,251 BTUs in this process from an ambient temperature of 62 degrees Fahrenheit to 212. This in a laboratory setting through observation and experimentation, enthalpy of fusion, pound of water from a solid to a liquid state. We don't go to the fire with ice, but it still needs to be distinguished between enthalpy of fusion and enthalpy of vaporization. I don't want to leave this subject yet to start talking about needed fire flow. We need to continue to look at some problems here to make it so it makes some sense to us. The author had asked a question back on page 8. Let's read something here. Suppose we're applying water to a fire. Let us assume that the water starts at 62 degrees Fahrenheit, and then when it's applied to the fire, it vaporizes. And this process is 62 to 212. We come up with 1,251 BTUs absorbed. Now look at example 1.5. How many BTUs will a gallon of water absorb going from a liquid state at 212 to steam at 212? Is there a difference? Is there a difference at water at 212 to steam at 212? What's the difference? Think about it for a minute here as you look back through the problem here. He's asking how many BTUs will a gallon of water absorb going from a liquid state at 212 degrees Fahrenheit to steam at 200 degrees Fahrenheit. Because we've already calculated the specific heat, we've already gone through that, we only need to determine how many enthalpy BTUs are needed for a gallon of water to change state from a liquid to a vapor. That's the difference. That's the difference here. At this first stage of boiling here at 220 degrees Fahrenheit, is still a liquid. What's happening here at this point here now is changing its state. It's a change of state here. And we know what that change of state is called, enthalpy. Changing from a liquid, see if I got it spelled right. What is a formula then? We're a people all about formulas, aren't we? What's a formula that we could come up with? And he's got the formula on page 8. Specific heat. The weight of water. The weight of water times the change in temperature. To find specific heat, the weight of water times the change in temperature. Will that help us in the problem at hand on example 1.5? Yes, it will. The formula of enthalpy of vaporization is the weight of water times 970. What is that? Where did we get this figure here? 970.3. I pause for a minute, let you look back at the top of the page. When a pound of water goes from a liquid state or liquid form at 212 degrees Fahrenheit to steam at 200 degrees Fahrenheit, it absorbs 970.3 BTUs, just changing state. This is per pound. Again, I challenge you, and I'll put it out as a discussion question. Where did the author come up with 1 pound of water absorbing 970.3 BTUs in a change of state from 62 to 212? And you notice you're not in the classroom setting, but you're watching me. What did I do wrong here? We'd already proven that this change of state, this latent, this enthalpy of vaporization, and you caught me, I've been around too many years in the fire service, you caught me saying the same thing I told you not to. Latent heat of vaporization, we're going to get away from that. This change of a liquid state to a steam state is enthalpy of vaporization. We've already done a problem here where we said 1,251 BTUs were absorbed in this process. Now we're talking about a change from 212 degrees Fahrenheit to 212 degrees steam. Where did the author get this figure here? That water changing the state here from a liquid of 212 degrees Fahrenheit just before boiling to steam at 212, we've got a figure of 970.3 per pound, 1 pound of water, 970.3 BTUs. We'll put that as a discussion question on you'll see it on the site. I'm going to be working with discussion questions, and I want someone to research it and find out where the author come with this figure. Is it just a laboratory figure, or can we prove that that's exactly how many BTUs? In our next session, if I don't get any responses, we'll research it ourselves. But I want someone to research that for me and find out where the author comes up with that figure. And it's an important figure because we've got to know that. We can't just say that we're going to the fire and absorbing 1,251 BTUs, because that's just going from ambient of 62 degrees Fahrenheit to 212. The water has not begun to put off steam yet. So we can't just use 1,251. We've got to add that 970.3 because it's changing from a liquid to a steam. Here, from 60 degrees Fahrenheit ambient to 212, it's at that stage of boiling, but it has not begun to put off steam yet. It's absorbed 1,251 BTUs. From this process, in a laboratory setting, we've determined from 212 to 212 putting off steam, there's 970.3 more BTUs absorbed. So you can see that you're going to have to do some addition there. And there's another question that we've got to always think about. We don't go to the fire scene with our thought process of how many pounds per gallon of water we're putting on. We're talking about gallons per minute. So we've got to do some more math involved here. I'm going to leave this one up. I'm not sure that it would, if someone came to this, I'm going to erase this. I don't think if anybody came to this mess that I've got here would figure anything out. So let's go back to a blank page here. You've got it recorded. You can go back several times and look at it. So let's look again at example 1.5 on page 9. If I've got you totally confused, then write me a discussion question and we'll go forward from there. Hopefully you can rewind and you'll be going back and forth looking at what we've done so far. Example 1.5 is how many BTUs will a gallon of water absorb going from a liquid state at 212 to steam at 212? Pound. We do not discuss pounds at the fire service, but the question is asking how many BTUs will a gallon, 1 gallon, absorb going from 212 to 212 Fahrenheit to 212 steam. What do we know about enthalpy of vaporization? We got a formula. Remember? We got a formula that says specific heat equals the weight of water times the change in temperature. What's the weight of water? 1 pound of water weighs what? Or 1 gallon of water. 1 gallon of water weighs what? 8.34 pounds. In my calculations and in the author's comments that we're asking for discussions about, he's given us a figure of 970.3 BTUs absorbed in that change of temperature from 212 degrees Fahrenheit liquid state to 212 to steam. 970.3 BTUs absorbed. If 1 gallon of water weighs 8.34 pounds times this change in temperature and what occurred in that change of temperature here, and the author has already done the multiplication, and you can check him out, 8,092 BTUs absorbed. That's the enthalpy of vaporization of 1 gallon of water. And we've been talking about change in state. 1 gallon of water, change in state of steam, 8,092 BTUs absorbed. 1 gallon of water. Example 1.6 on the same page then to follow through with that. How many BTUs absorbed when a gallon of water goes from ambient temperature to steam? We're going to go follow this program or this example just out of the book. Remember back in example 1.4, and I'm going to erase this. You can go back forth to it, but I'm going to erase this so I've got a clean slate here. We've already, if you look back and think about what we've already determined so far, example 1.4 says how many BTUs will it take to raise 1 gallon of water from to 212 degrees Fahrenheit and not vaporize it. And we came up with a figure of 1,251 BTUs. That's going from 62 to 212, but not vaporize it. Okay, we'd already determined that. The question now is asking how many BTUs is absorbed when 1 gallon of water goes from ambient temperature to steam. It hasn't gone to steam yet, right? At this point here, 1,251 from here to here is not going to steam. But what do we know about 212 degrees Fahrenheit to 212, putting with conversion of steam. Latent heat of vaporization there, 8,092 BTUs. And we got that. We've already worked that problem out in example 1.5. So you're going to have to follow these in step. When you look back at example 1.4, the next one is example 1.5, and now example 1.6 to get an answer that is useful to us from this point on. (9,343 BTUs per gallon of water is absorbed. Again, 9,343 BTUs are absorbed from a liquid state to a steam state. 1,251 from 62 ambient to 212, then from 212 to steam, 8,092, add the two together. This is the figure that you'll see in your computation from this point on, because we had to go step by step to come up with this, but that's the figure that you'll see. 1 gallon of water through this process of enthalpy of vaporization will absorb 9,343 BTUs. Okay, let's go to page 10 in the textbook and look at another term. I'm not sure that I have that term, but needed fire flow. It's calculating this needed fire flow. And this is, if you call it an acronym, this is the symbol that you'll see in most of your textbooks, the NFF, the needed fire flow. Estimation of the amount of water in GPMs needed to extinguish a fire in any specific building. And there's a formula for that. The gallons of water equals the BTUs given off divided by 9,343, which we just went through 3 steps of determining that figure, 9,343 BTUs, that are absorbed. And think about some terms that we see in the fire service. Exothermic versus endothermic. We say that fire is an exothermic reaction. It's a heat reaction that gives off heat. An endothermic reaction is one that absorbs heat. So this reaction where we can vaporize water at this enthalpy of vaporization, this process of endothermic means we can absorb BTUs, and we know how that can be helpful to us in the fire service. So now we've got a means by where we can come up with a formula. A needed fire flow equals the gallons of water we need, or the gallons of water that we are applying, equals to the BTUs given off divided by 9,343 BTUs. And let's follow through with that formula with a problem. On page 10. Go with me here as we read a little bit here so that you can follow it with some sort of concept here about needed fire flow. The practical applications that we went through, examples 1, 4, 1.5, and 1.6. It tells exactly how much heat a gallon of water will absorb. Here, 9,343. We went through that. When it is vaporized, enthalpy of vaporization. This NFF, needed fire flow, is an estimation of the amount of water needed to extinguish a fire in a specific building. If we know the potential BTU output of the fuel burning, and do we know that? There are figures and there are journals and there are textbooks out there that will give us there's certain amount of BTUs that certain amounts of fuels give off. Class A, B, C, D. And we've got that out there. That's already, again, applied science, and it has been determined, and there are charts out there that tell us. If we know the potential BTU output of the fuel burning, we can easily find the amount of water needed to extinguish it. Simply divide the potential BTU output by this 9,343 to obtain the gallons of water necessary to absorb the BTUs given off. So we've got that formula. How many BTUs are given off is dependent upon the fuel that's at the fire. And if we know that through this process of enthalpy of vaporization, we can absorb 9,343 per gallon of water, we can divide 943 into this BTUs that's given off at any specific time during the building and come up with a gallon of waters. And that's a simple formula to this point, and we'll add to it. The author puts a catch there. He wants you to note that. There are a couple of catches. The water must be applied all at once and must be applied directly to the burning material so there's no runoff. Can we do that? Is there ever a time that, we don't go to the fire as a deluge sprinkler type system, so we're not applying all of the water at one time and we can't control the amount of runoff. So that's one catch that he points out. So this method of calculating how much water is needed to completely absorb the BTUs given off assumes the fuel is consumed all at once. And again, that's a catch. It's not consumed all at once, right? Fires burn over time. Therefore, the BTU output is spread out over time. More practically, we only need to absorb the amount of BTUs being given off at any point in time to extinguish a fire. So note that before you go saying, I caught him. He wants us to understand this concept is not something that it's not impractical, but we need to look at it as how it is practical to us in the fire service. So calculating the fire load. Notice on page 10, and I said I wouldn't read, but I want to read with you here. When calculating the fire load, the amount of combustibles per room or structure is given in pounds of combustibles per square foot. Pounds of combustible per square foot. Dimensions. We talked about a room, length time width, whatever, a 10 by 10 room, 10 by 12, small bedroom. That's 120 square foot area in this bedroom here. What do we know the combustibles that's in that room? Possibly we've got it identified. There's furniture in there, so there's Class A fuels in there as a whole, Class A fuels. The author looks at, again, he's going back to a reference in some scientific book that he's pulled out. A bedroom is calculated at 4.3 pounds of combustible per square foot. .3 pounds per square foot in a common bedroom. That's a given that through laboratory settings, someone has done some calculations with those Class A fuels there and how many BTUs per square foot would we expect in an average bedroom. And we'd have to use the term average because they know that there could be instances where someone's got something else hidden in a particular bedroom. That's just the bedroom, 4.3 pounds per square foot for the bedroom. The fire load of the entire room is calculated by multiplying the fire load per square foot times the area of the room. I should have made the example like he's got in the book, so I'll follow through with that. He's got 15 by 15 room because he's got 225 square foot in his bedroom in the example in the book as we follow with him. So he's got a room that's 15 foot by 15, length, time, width, dimension-wise, 25 square foot bedroom. If you take this 225 as the square foot of the room times the 4.3 pounds per square foot, we come up with a figure of 967. Fuel load. Notice the formula that he gives us in the book. Fuel load equals the area times. Now what's the difference here? This small FLD and the capital letter FLD. Notice that this is the area, and we get area by length times width, a square foot area. The area is the area that he gave us of 225 square foot in that bedroom. The FLD is the fire load per square foot. We've already determined that he's given us that figure of 4.3. Notice that that's 4.3 pounds of combustibles. And evidently they're coming up with an average figure here of an average room. We're saying that an average bedroom would have 4.3 pounds per square foot of combustibles. So 225 times 4.3 will come up with the figure that he's already done the multiplication for me, 967.5. Now, and does that give us any indication about how many BTUs? What does that give us an indication of? It gives an indication of exactly what the formula says, a fuel load. We have a fuel load now of 967.5 pounds of fuel load in this 15 by 15 bedroom. Is that going to be of any value to us in the fire service? Look at example 1.7. How many BTUs will be given off by this 967 pounds of ordinary combustibles? That's the first question. Then he asked how many gallons of water are needed to absorb that total BTUs given off. And we've got to go back, though, to some of our problems that we've already worked to do this, right? Example 1.7 and on page 11. The first part of the question says, how many BTUs will be given off by 967.5 pounds of ordinary combustibles? That's the first part of the question. How many BTUs per pound does ordinary combustibles generate? Again, that's a laboratory setting that someone in a laboratory setting has come up with a figure of 8,000 BTUs per pound. 8,000 BTUs per pound of ordinary combustibles generated. Ordinary combustibles generate 8,000 BTUs per pound. So if this room, this 15 by 15 room that we worked out, 225 square foot, has a fuel load of 967.5 combustibles in that room, and each pound gives off 8,000, then if you do the multiplication, and he's fortunately already done that for me. And you're following it with me in the book. You see the extreme number of BTUs that we are coming up with a figure here. This is just a 15 by 15 bedroom. Ordinary combustibles, 7,740,000 BTUs. Okay, that was the first part of the question. How many BTUs were given off by 967.5 pounds of ordinary combustibles? Second part of the question was how many gallons of water are needed to absorb the total BTUs given off? And that's what our part in the fire service comes to, right? Our part is by applying water through this latent. Y'all gonna catch me over and over again. I've been in the fire service over 30 years, and that latent heat of vaporization. I hope before we get through that even with my mistakes of using the term, that you will quit using the term latent heat of vaporization. Every textbook that I've seen use in the fire service uses latent heat of vaporization. It's enthalpy of vaporization. We've changed the state of water at an ambient temperature coming to the fire scene to steam. We know we've got already done the problem. We've come out with how many BTUs we can absorb. I'm running out of space here. 9,343 BTUs can be absorbed per gallon. So if we divide 9,343 BTUs absorbed into this total BTUs that's in the room of 7,740,000, the author has done the work. I'll just write what he's come up with. 828.42, or rounded off 828 gallons of water. Now, do you want to flood a bedroom with 828 gallons of water? Don't catch me in something like that. We're not going into the bedroom and flooding that bedroom with 828 gallons of water. So there's some thinking that you need to be involved in here. And again, this applied science is practical to us. We can see how much BTUs are being generated, and we can see what we can do with water. But I don't want anybody to go into a bedroom and flood that bedroom with 828 gallons of water. I want us to consider what can be done here. Okay, let's look back at some of our definitions that we've come across so far. We've talked about needed fire flow and how we could come up with a formula. The gallons of water that's needed is the BTUs given off divided by 9,343 BTUs absorbed by this latent process. How many people caught it? You're not in front of me. You're out there. It's enthalpy of vaporization, not latent heat of vaporization. I'm going to say it over and over again. Fire load, the amount of combustibles per room of a structure, and we got a formula for that. And we went through several examples there. We talked about exothermic and endothermic reactions. Exothermic heat, a reaction that gives off heat. An endothermic reaction is one that absorbs heat. So let's look at this process of conversion of water to steam. Through this process of enthalpy of vaporization, we're changing water from liquid state to steam. Remember we started off talking about dimensions. We took a little old box, a cube here, and we said that cube was 12 by 12 by 12 inches, 1 cubic foot, and we converted that into inches. And the reason why, and think about why that I want you to start thinking about cubic foot being converted into cubic inches, because we deal, in the fire service, we're dealing with pounds per square inch, PSI. You're going to have to have that concept in mind about a cubic inch and the concept of cubics. So in this formula here, to find the volume of that cube, length times width times height, whatever that dimension is. The second point is 1 gallon of water will expand into 227 cubic feet of steam. So what we want to know is how we can come up with a formula, the gallons of water needed to fill a room with steam. And that has been provided for us through this process here of 1 gallon will expand 227 cubic feet of steam. We can figure out the volume divided by 227 and come up with the gallons. And in the fire service, we talk about gallons per minute. So it goes down to this figure of volume divided by 100. And I know you've seen that out there, that figure there, talking about conversion of water to steam. Page 11 in the textbook is the author goes through an extensive explanation of this process of conversion, and then we look at a problem, an example. And that example is example 1.8. How much water is required to completely fill a bedroom on fire with steam if the room is 15 by 15? Volume, length, time width, time height. If it's 15 by 15, does he give us the height? And he does in the formula. He doesn't speak of it as being height, but he gives it as 15 by 15 by 8. So we've got a 15 by 15 room with an 8-foot ceiling. These are foot. And we'll come up with a volume which will be in cubic feet. 1,800 cubic feet volume in this room. That is 15 by 15 by 8. So we've got 1,800 cubic foot volume in that room. Now determine the gallons of water is needed. First divide the volume of the room by 1,700. And we've got to go back in those examples. That conversion rate of 1 to 1,700. 1.059. Don't get caught in the trap. If this 1,700 is in cubic feet, and this 1,800 that we figured here is in cubic feet, this answer is going to be in cubic feet. So 1.059 cubic feet. Do we go to the fire service with cubic feet on our mind? No. But that's what we've got. We've got this volume of 1,800 cubic feet bedroom here, and we've converted that water to steam, and it's filled up that space at 1,700 per 1 cubic foot into 1,800. So we say that we've got a figure of 1.059 cubic foot of water needed. How many gallons of water this figure represents? We've got a formula. Look at the page 11. The gallons needed equals the volume times 7.48. Where did we get the 7.48? 1 cubic foot of, well, one cubic foot of water, and I told you that some of these need to be memorized. So in that physical properties of water, 1 cubic foot container will hold 7.48 gallons. So if we've got a volume here times 7.48, the volume of water that we needed was 1.059 times 7.48. Well, we're converting this that is in cubic foot of water to gallons. And the author has done the multiplication. You can check his work. 7.9 gallons of water. .9 gallons of water. So look back at what the problem or the example was asking. How much water is required to completely fill a bedroom on fire with steam if the room is 15 by 15 by 8? And that's a far cry from that 828 gallons that we come up with a while ago. Keep this in mind. Keep it all in mind when you're looking at this coursework here to keep it practical and keep it in the concept of 7.9 gallons of water will convert and fill this room with steam, which will blank out a fire in some instances. Just think about, once you understand the concept, it's possible to make direct calculation of the amount of water that we need to fill a given volume with steam, any volume. And so example 1.9 on page 12, if we use the formula here of the volume of the room of 1,800 cubic feet and the volume divided by 227, .9 gallons again. Think about what the author is doing here. He's showing us another way to get the same thing we just come up with the formula of volume divided by 227. We know through one of the earlier problems there that you hopefully will go back and look at, that we've got, look at example 1.9. We calculate the volume of the room, 1,800 cubic feet, 15 by 15 by 8. A gallon of water will expand to what? 227 cubic foot of steam. So we've got a 7.9 gallons. We've done it two different ways here and come up with the same answer here of finding out the water that we would need in gallons. And it depends on which one that you, if you're, okay, in what conditions and in what kind of circumstances would 7.9 gallons of water be sufficient for this volume of 1,800 cubic foot, a 15 by 15 by 8 room? The author wants us to note and be a word of caution. On page 12, he points out the room in question that we were talking about would have to be first unvented. It would have to have a perfect conversion of water to steam. And we know that these conditions do not occur at real fire. So this is just an example. So don't go back and tell someone this is all I need. Keep in mind the author is constantly pointing out that every fire is different. Every fire has different fuel loads. We know that the fires get vented and various things occur. So look at these as a means by determining at what realm this is an applied science and at what sense is it practical. There are formulas that have been devised here that you'll notice, and you see it in a lot of the textbooks out there. This one that the author points out, Arroyo and Nelson determined that 1 gallon of water will be produced 200 cubic foot of vapor and steam and still have a margin of safety. And then that he goes on further to say that these two that were doing this, again, in a laboratory setting, and they were able to determine from exhaustive studies of live fire tests that the greatest extinguishing efficiency was realized when the water flow was sufficient to accomplish extinguishment in 30 seconds. This led the team to develop this rate of flow formula of GPMs equals the volumes divided by 100. And this is the formula that you've seen out there. Volume, GPM needed. And look at that then in the case of here, 1,800 cubic foot divided by 100, 18, and this is in gallons, right? How many BTUs will be absorbed by this formula here of those two that worked on this study, this 18 gallons of water being put onto this volume of 1,800 cubic foot, 15 by 15 by 8 room. The example that we already looked at says that we determined a gallon of water will absorb 9,343 BTUs. Per gallon. Times 18 then. And we'd come up with a figure. But remember that the author wants us to point out that this in 30 minutes should be half of that, 9 gallons. Because the hour formula expects the water to be applied, and we're looking now at example 110, applying the Iowa State rate of flow formula. The room that we looked at, 15 by 15 by 8, 1,800 divided by 100, come up with 18. The difference, this is per minute, and we're looking at 30 seconds. Half of that would be not the 18 gallons, but 9 gallons. And take that 9 gallons then times the 9,343 absorbed and come up with the figure that he wants us to look at here of 84,087. 9 gallons here using this formula times what's absorbed when it changes to steam, 9,343, and come up with BTUs absorbed, 84,087. Hopefully we'll, and I cautioned you to constantly, you'll have the advantage. If I was in a classroom setting, you could ask questions. So remember that if you can flip back, all of this is recorded, so as you flip back, look back at the examples. So examples 1.5, example 1.6, example 1.8, 1.9 that we worked on, so that you'll have a sense that this is all going to come together to some meaning to you. Volume. We looked at a container at a cubic foot, and we said that volume times 7.48 will give us a gallons. And what do we want to get out of this? Now we're looking at how we're going to calculate, and whether or not it would ever be of use to you or not. There are cases where you might be determine how much water would be utilized to fill a swimming pool. In this case, we don't go about filling swimming pools, but it might be a container or some type of, and later on we do fire flow, we're talking about storage facilities and where we store millions of gallons of water. Here's a formula that is volume is length times width times height that we've already looked at, and then to calculate the gallon of water is contained in a given size container. Once that we know the cubic feet, the volume in cubic feet times 7.48, because there are 7.48 gallons per 1 cubic foot, then we can find the volume of any container. And that's, I don't want to extend you past what, I want to be an exercise of math for you, but look at example 111. What's the volume in cubic feet and gallons? What is the volume in cubic feet and gallons of a tank that's 10 feet long by 5 feet wide by 1.33 feet deep? And you can go through that process of multiplication that we looked at the formula here. If we know the volume, we can find the volume by length times width times height. They've given us the dimensions of the container. When we multiply that out, we come out in a volume in cubic feet. And then we know how many gallons per 1 cubic foot. And in that particular problem, you can work it out and you can come up with how many gallons of water it would take to fill up that container. And you can look at that on your own. There are also some other problems here that can get let you look on at your convenience to look at. Remember one thing, that this formula for volume, length times width times height, is always dealing with squares and rectangulars. It's not cylinders. There's another formula out there for finding the volume of a cylinder. And we need to look at that because the majority of our storage tanks are cylinders. Look at page 16, looking at a formula then to give the cubic feet volume of water in a cylinder. In this case, what's the area of a circle? Any of you that remember your math, to find the area of this circle, when we talked about a rectangular square, it was a length times width. To find the area of this circle here, in all of our schooling, we've learned that to find the area of a circle is pi, which is a constant, 3.14 times the radius squared. Now in the fire service, we don't think of a radius of a circle, which the radius is here. We think of the diameter. When we talk about the diameter of an opening of a hydrant opening or fire hose opening, a nozzle, we talk about the diameter. So we need to have a formula that deals with diameter. and the author and any of you that want to look through his reasoning, but we could do it. But if pi is 3.14 and this radius, what could we substitute for the radius? Anybody? Are you following me in the book? We know that the radius is what? Can we see that the radius is the diameter divided by 2? If the radius is this distance here from here, the diameter divided by 2. In any case, any dimension you want to put in there, we can do by a matter of substitution, we can substitute for r radius the diameter divided by 2. And if we do that, then square it the same as this formula here, we can come up with another formula here. And through means of mathematical (3.14 times diameter squared divided by 4), divide 4 into 3.14, and you come up with a constant of 7.854 times the diameter squared. Now we've got an area of circle that we can utilize in the fire service. You see my dot, it's supposed to be here. Okay. I'll get it right in a minute. 0.7854 times the diameter squared. The area of a circle then that we will utilize in the fire service will be that formula to find the area of a circle. Area equals 0.7854 times the diameter squared. And we haven't done anything injustice to it. It's the same formula. Anybody want to try it, put any figure you want to in there for radius and diameter, and you're going to come up with the same area there. So why are we concerned about cylinders? And you see I'm not an artist, but if this is a cylinder here, if we that's vertical. What if we put this cylinder horizontal? It's nothing more now than a fire hose or any type of pipe in our hydrant systems. Any underground pipe is a cylinder. And so now we've got a means by which we can find a formula to find how much volume of water is in a fire hose. And that's what the author is looking at, the math computation on page example of 113 on page 16, how much water is in a 50-foot section of charged 2.5-inch hose. And he's given us a formula. And again, as you look through formulas that we use in the fire service that you've seen throughout your training, this is nothing new to you, but think about what formula that you use at your training station and how we got to that formula. And the author gives us a step-by-step of how, and it might be that when you walk into the fire station and begin to do some training, and your training officer, training instructor gives you formulas and tells you to work out, have you ever asked him, well, where did you get that formula? And maybe you got the question, the answer you got was just do the problem. Well, the author has given us some good insight as to where these formulas that you see around your fire station came from. This formula you'll see out there, 5.87 times the diameter squared times the length, to find how much water is in a 50-foot section of charged 2.5-inch line. If it's a charged 2.5-inch line, what's that 2.5 tell us? 2.5 tells us it has a diameter opening of 2.5. and it's a 50-foot length. And we've got a constant here of 5.87. That's the portion there that often, if you ask why, that they say, I'm not sure what answer you'll get, but if you will just do the problem, that you'll come up with the volume that's needed here. Well, the author has given that to you. Look through it. I'm not going to take the time. It's right here in the book. He's given you a step-by-step of where he came up with his 5.87 constant in this problem. Again, it'd be a good point to look at as a discussion question for you to look at and follow through with that and send me as a post how that 5.87 constant came from. How much water is in a 50-foot section of charged 2.5-inch hose? Work the computation out, and it comes up to 12.6 gallons of water. So, and you know yourself that 12.6 gallons of water weighs how much? If you have listened and probably through process of time that figure should be in your mind. How much does 1 gallon of water weigh? 8.34 pounds. So 12.6 gallons times 8.34, we've got 105 pounds. So we see we got quite a bit of weight there in that section. And the author also even does some more computations there and gives us a formula whereby you can look at, and this one you've probably seen out there at the fire station. Where you're not having to do the conversion now. You just got one formula where you got the 2.5 times the length of a 50-foot hose, and now you've got a constant of 49. And the author explains how through process, look through it. If you have any questions, send me a post and we'll go over it. So what we've been doing here is some exercises in math. I understand that, and some concepts of physics. And so as you begin to go through the course, it's going to get more extensive into this. This is just chapter 1. We're going to go through a process of possibly answering some questions that you might have asked or afraid to ask as to where these formulas came from and what good are they us in the fire service and how to apply them. The author does give us this note of caution, and I think it's, and here, when you get to this slide, go through it, look through it. I'm not rushing, but I want you to realize that some of this I've already worked out for you, and you can see how that you can come up with the constant here of 49. You can come out to the constant of 587 through math computations here. Final note that the caution, and we do need to look at this because we're a people in the fire service. If you haven't, and I don't think I'd be wrong in saying that, but you have possibly. If we see something in the fire service that says 7.48 gallons per cubic foot, well, it's a lot easier to multiply 7.5. So if you change that 7.48 to 7.5 in your multiplication, your final answer is going to be different than what's in this book. And some of you might have already noticed that some of the rules of thumb, some of the figures that you use are different than this author. So some figures are given as standards in this book will not agree with other references. Figures in this book represent a recent calculation. Older figures have been replaced with results of recent calculations, and that's what the author wants to figure out. You'll notice in all of his work that he is rounding it off to two numbers, 7.48 to the hundreds. He's not rounding off to the tenths. And in the fire service, would it matter between 815 gallons per minute between 805? No, but the author is emphasizing that this is an applied science course, and through this experimentation and observation, he wanted these recent calculations in this textbook. A quick summary then is on, and I won't read it. You've got the advantage of where you can, this is recorded now, you can go through all of what we've got and go back over and over again. This is a good summary here has been put for you in the slides here. So look back through as many times as you need to, go back through the summary, and remember that this study of hydraulics is an applied science. It's not a theory. And we don't make the mistake of someone say, oh, you're taking that theory course, theory of hydraulics. No, you're taking applied science, and there's going to be more math involved, more physics, and just be prepared. This is chapter 1. Next week, you'll see chapter 2 out there for you. If there are any questions, you've got access to the learning management system we're using here at Albany Tech is Angel Learning, and we also have an eLearn site there developed. You have access to those sites, and you can post discussion questions, and I'll be posting discussion questions, and you can send back responses to me. So have a good day.